In space, time flows differently in various situations. For example, near a black hole, time will pass more slowly, while on Earth, millennia can go by. But in this dark sphere, only moments have passed. It has been over 100 years since Einstein's theory of relativity shook our understanding of time and space. But how does it actually work? And what is space-time? To all of us, time and space seem so ordinary. We talk about spending time, say that time flies like an arrow, or, conversely, that time drags on. But in any case, time, like a river, flows from the past, through the present, into the future. As for the space around us, we don't say anything similar. Despite the ubiquity of time and space, there are still many unanswered questions, to which Einstein's theory is just beginning to provide answers. Many of us perceive space as something abstract and distant. However, space is omnipresent. It is everywhere, just like time. But what is space? For example, Newton conceived space as an empty theatrical stage. Newton's represented stage was absolute, eternal, unchanging, and passive. By defining space in this way, Newton was able to describe the world in a way that no one had done before. It was an immovable stage that helped him understand all the motions we see around us. It's this immovable stage that allowed him to predict everything, from apples falling from trees to the path the Earth takes around the sun. These laws work so precisely that we still use them today when launching rockets or when pilots take multi-ton planes into the sky and land them safely. All these laws tell us that space is real. Even though we can't saddle it or feel it in any way, it's still real. In the early 20th century, new theories emerged that slightly undermine the foundations of Newton's stage. These theories were proposed by Albert Einstein. It wasn't street lamps and lanterns that caught Einstein's attention, but the nature of light itself. In particular, what intrigued Einstein was one unique property of light: its speed. The speed of light had always been a mystery, and Einstein wondered why electricity and magnetism didn't adhere to Galileo's principle of relativity. This eventually led to Einstein's theory of relativity. In this theory, Einstein proved that the speed of light is always constant and the same for everyone. Here's how Einstein explained it. Knowing that speed is a measure of space in which something moves through time, Einstein proposed a staggering idea. He suggested that space and time can interact with each other, constantly adapting so that no matter how fast you're moving, when you measure the speed of light, it will always be the same because it's equal to 1,079,252,850 kilometers per hour. According to Einstein, space and time are no longer considered constants and absolutes. Instead, they merge with motion to form a unified entity called spacetime. This revelation led Einstein to solve another puzzle related to the most significant force in the universe: gravity. It took Einstein another 10 years to reach a sensational conclusion. He discovered that the secret of gravity lies at the core of spacetime, which turned out to be even more flexible than Einstein had previously thought. Einstein discovered that gravity is the deformation of spacetime caused by objects within it. In other words, gravity is the very essence of spacetime itself. For instance, the moon orbits the Earth not because it's attracted to some invisible force from the Earth, but because it follows the curvature of spacetime created by the Earth. Einstein found that the space that Newton saw as passive was, in fact, dynamic. It is woven into a unified fabric with time and dictates the laws of object motion. After this revelation, it was impossible to think of space as a static stage. But is that the reality, or is it just a metaphor? Does it describe what space is actually like? Einstein's theory predicts that to find out, one must journey to the edge of a black hole. Gravity around a black hole is so strong that, according to Einstein's calculations, a spinning black hole can stretch and twist space as if it were a piece of fabric. The problem is that the nearest black hole to us is 27,000 light-years away, making it difficult to verify this assumption. It wasn't until 2008 that scientists managed to conduct an experiment confirming the correctness of Einstein's calculations, showing that space is indeed a physical reality, akin to fabric. This raised several more questions. What is the fate of the universe? Will space continue to expand indefinitely, or will gravity halt the expansion, causing it to contract inward? To find answers to these questions, astronomers decided to measure the slowing down or expansion of the universe using a non-standard tool, exploding stars called supernova. scientists found that space isn't contracting but expanding. Thus, they concluded that there's something filling space and pushing galaxies apart, thereby stretching space. This mysterious substance was named dark energy. It turned our understanding of the universe upside down. As it turns out, more than 70% of the entire universe is composed of this enigmatic dark energy. This expanding universe makes the curvature of spacetime even more challenging to grasp because the equations show that space's expansion is infinite, causing the universe to become less dense as a result of this expansion. One thing is clear: this reduction in density is not entirely uniform. Some galaxies hold together while others collide. But what happens at the boundary between expanding and non-expanding space? This question remains a headache for scientists, because space's expansion makes the shape of yesterday's spacetime different from tomorrow's spacetime, thereby violating what was considered one of the key properties of the universe, the conservation of energy. The importance of symmetry in physics was elaborated by mathematician Emmy Noether. In this case, symmetry means that changing an object's location doesn't alter its physics. This implies that momentum is conserved. The fact that physics today and tomorrow are the same is an element of energy conservation. However, in an expanding universe where space and time change, this symmetry is broken. When photons travel through an expanding universe, they don't stretch and lose energy. Thus, energy is simply not conserved as space expands, and this puzzle still troubles physicists. So now it might seem that space has finally become physical and real. We have learned that it can bend and expand. With the advent of Einstein's theory of relativity, physicists faced a new challenge. They knew that every particle in the universe has a past, present, and future. Similar to drawing a line on a map, they could trace a particle's journey through the 4 dimensions of space and time, following its path from the past to the future through a series of present moments. Each particle in our bodies, every electron or quark, travels along its own line. But before you were conceived, these lines were dispersed, and after your birth, as you grew, these lines converged into a bundle, which is you. When you cease to exist, these lines will disperse once more. Here, it's essential to understand that our life is but a moment in the scale of the universe. We exist as a set of lines in the fabric of spacetime. Due to Einstein's theory of special relativity, space and time are more complex than Newton once imagined. But space and time remain universal. This universality is violated when considering the curved spacetime of general relativity. It's important to realize that, in general relativity, space and time are dynamic and evolving. They are not just a stage, as Newton pictured them. They are active players in the physics of the universe. However, because the unification of gravity and quantum mechanics was not achieved, some physicists began to search for answers elsewhere. These searches led to a new theory called the theory of everything. Until now, fruitless attempts to link the microscopic quantum world with general relativity to fully explain the universe had yielded no results. Thus, other theories began to emerge. One of the leading contenders for the truth is string theory, or M theory, which may involve 11 or even 26 dimensions. But what do these theories say about the fundamental nature of space and time? Here again, it's not so straightforward. In M theory, space and time are part of the fundamental structures of the universe. The bizarre, curved form of this multi-dimensional structure explains everything, not only space and time but all matter as well. However, M theory doesn't reveal what these structures are made of. Another contender for the theory of everything is loop quantum gravity. At first glance, this theory is even more peculiar because it suggests that space and time are quantum phenomena. For example, on the tiny Planck scale, spacetime is envisioned as a fine network fundamentally connected to each other. To us, this subatomic network appears as smooth space. Again, the question arises, what is this quantum network made of? And again, we encounter a lack of answers. But perhaps we've made it all too complicated. Maybe it's much simpler. Some scientists suggest that space and time may not exist at all. Everything we see, including space itself, might be akin to a hologram. In other words, everything we perceive and feel could be a projection of information stored on the surrounding surface. This theory is so new that physicists are still trying to grasp it. But if it holds true, then like Newton and later Einstein, who completely revolutionized our view of the world, we may be standing on the brink of an even more dramatic revolution now. Because space, an integral part of our everyday life, remains a familiar stranger. It surrounds us everywhere, yet we are still far from unveiling its true nature. This could take another 100 years or perhaps 1,000 years, or it might happen tomorrow. But when we solve this puzzle, we will take a significant step towards fully understanding the mysteries of the cosmos. Well, I would like this mystery to be unraveled in the coming decades. For now, all we can do is wait for new discoveries. To all who watched this video until the end, thank you for watching, and until our next, even more intriguing encounter.